All right, let's talk about 2012. The world of physics was absolutely buzzing over the discovery of the Higgs boson. You know, the God particle. It was supposed to be the final piece of the puzzle, the capstone of our understanding of, well, everything. But what if that wasn't the end of the story? What if it was actually the first chapter in a completely new one, something way more radical? Let's dive into that story and see what secrets that famous particle might still be hiding.
I mean, you have to picture it. For years, you had thousands of scientists at the Large Hadron Collider in Switzerland just smashing particles together at mind-bending speeds. And the whole goal was to find this one single missing piece of their master theory of the universe, the Standard Model. Then, in 2012, they finally stood up in front of the world and said, "We got it."
And what they got was this, a brand new particle with a mass of 125 giga-electron volts. Now, that's just physicists speak for incredibly heavy. But that number, 125 GeV, that was pure magic. Why? Because it landed precisely, and I mean precisely where the Standard Model predicted the Higgs boson would be. This wasn't just a discovery, it was this incredible confirmation of decades of theoretical work. Just a moment of pure triumph.
So yeah, the discovery was celebrated, Nobel Prizes were handed out, the textbooks all got updated. But you know, in the quieter corners of theoretical physics, a totally different question started bubbling up. What if the particle they found wasn't just another cog in the machine, but what if it was the first time we actually got a glimpse of the machine itself?
Okay, so to really wrap our heads around this wild new idea, we first have to get a solid grip on the accepted one, the brilliant and, honestly, unbelievably successful Higgs mechanism.
So the Standard Model tells us that the entire universe, all of space, is filled with this invisible energy field, the Higgs field. As fundamental particles try to move through it, they interact with it. Some, like a photon of light, just zip right through without a care in the world, and that's why they're massless. But others, they get kind of bogged down. They experience this cosmic drag. And that drag, that resistance to moving, well, that's what we perceive as mass.
And that's why finding the Higgs boson, the actual particle of this field, was such a massive deal. It was the last missing puzzle piece. It perfectly explained why some of the particles that carry forces are super heavy while others are light. It basically put a giant checkmark next to a core concept of modern physics. For all intents and purposes, it felt like the perfect ending to the story. Or was it? Because for all its power, the Standard Model has some pretty deep, kind of unsettling cracks in its beautiful armor. It's an amazing story, for sure, but it's not the whole story.
And that kind of begs the question, right? If the theory works so well, why isn't everybody just, packing up and going home? Why keep searching for something deeper? Well, it's because the Standard Model leaves some of the absolute biggest questions about our universe completely unanswered. And listen, these aren't just minor details we're talking about. The theory has no clue why gravity is so ridiculously weak compared to the other forces. It predicts an energy for empty space that is, and I'm not exaggerating, catastrophically wrong, like 120 orders of magnitude wrong. And to make the math work for particle masses, it relies on these totally arbitrary fudge factors called Yukawa couplings. They're basically just magic numbers that physicists have to plug in by hand, with zero explanation for where they come from. So the model works, but it doesn't really tell us why it works.
And this, right here, this shows you the hierarchy problem perfectly. On one side, you've got the neutrino, which is almost nothing. On the other, you have the top quark, this absolute behemoth that's about 17 trillion times more massive. The Standard Model can handle this, sure, but it gives us zero reason for why this insane gap even exists. It's kind of like having a theory of animals that lists both a tiny mouse and a giant blue whale but has absolutely no concept of biology or evolution to connect them.
Okay, so this is where a completely different theory steps onto the stage. It tries to reimagine the very fabric of reality itself. It's called Dynamic Vacuum Field Theory, or DVFT for short, and its starting point is that what we call empty space isn't empty at all.
Now this is a really fundamental shift in thinking, and it creates a whole new picture of reality. So the Standard Model sees the vacuum like a blank, passive stage, and all the particles are just actors performing their parts on it. DVFT comes along and says, nope, the stage is the actor. Everything we see, particles, forces, even gravity, it's not happening on the vacuum, it is the vacuum just behaving in different ways.
The absolute best way to picture this is to imagine the universe is this huge, invisible ocean. Now, this ocean has two main things going on. First is its amplitude. The theory calls it rho, which is kind of like the depth of the water or the height of the waves. DVFT says this is what creates mass and gravity. The second thing is its phase, called theta, which is like the rhythm of those waves, how they oscillate. And that's what creates all the other forces and all the weirdness of quantum mechanics.
And this is where it gets really cool, because this brings us right back to our particle from 2012. In this new model, the Higgs isn't some separate field that's just sprinkled on top of everything. No, it's simply the very first ripple we've ever managed to detect in the amplitude of the vacuum ocean itself. It's not some lonely particle. It's a wave in the very fabric of reality. So you might be thinking, okay, cool idea, but what's the big deal? Well, the really powerful thing here is that this one simple shift, this idea of a living, dynamic vacuum, seems to just elegantly solve all those puzzles that the standard model couldn't even touch. So how does mass work in this new picture? Forget that drag from the Higgs field. In DVFT, the vacuum itself has a natural stiffness. Particles aren't just little points. They're more like stable knots or structures within this medium. And these knots actually deform the vacuum's amplitude. The more a particular knot deforms the vacuum, the more energy it costs to exist. And that energy cost is its mass. Suddenly, you don't need any of those arbitrary Yukawa numbers. It's all just about geometry and structure.
And this is where it all just clicks together beautifully. Just look at this table. The mass hierarchy problem, the one that needed all those fudge factors in the standard model, here it just arises naturally from the vacuum structure. Gravity, which used to be a totally separate theory, now it just emerges from changes in the vacuum's amplitude. And all the other forces, they come from changes in the vacuum's phase. Instead of all these separate, bolted-on pieces, you get one elegant, unified system.
Okay, this all sounds incredibly elegant. Maybe a little too elegant. But a beautiful idea isn't enough in physics, right? To be taken seriously, a theory has to make unique predictions that we can actually go out and test. It has to tell us what to look for. And DVFT does exactly that. It predicts that other popular ideas, like supersymmetry, which propose a whole zoo of new particles, are wrong. The fact that the LHC hasn't found any of those particles so far actually supports DVFT. More than that, it predicts a totally new type of particle called a glue ball at a very specific energy range. And it predicts that if we can measure exactly how the Higgs particle interacts with itself, we'll see tiny differences from what the standard model says. These are real, concrete tests we can actually do. So this leaves us with a really profound thought. Maybe the 2012 discovery wasn't the end of a story after all. Maybe it was just the beginning of a much, much grander one. It's possible that scientists at the LHC didn't just find the final piece of an old theory, but the very first evidence of a new one. A theory that suggests we don't just live in the universe, but that we are literally part of a dynamic, living vacuum. The only question now is, what else are we going to find when we keep watching the ripples?